All right, the next thing I want to talk about are infinite limits, and the example that we're going to look at asks us to find the limit as x approaches 0 of 1 over x squared if it exists. Now, to see if this might exist, we're going to want to make a table of values where we have x values that are approaching 0 from both sides. But there is a little shortcut we're going to take, because here's the thing. When we look at 1 over x squared, we know that whether we take a negative or a positive and square it, we'll end up with a positive answer as a result. So whether we take a value for x that's positive or its opposite, we're going to end up with the same answer. So for our table of values, what I'm going to do is I'm going to write plus or minus 1, plus or minus 0.5, plus or minus 0.1, plus or minus 0.01, and plus or minus 0.001. And that plus or minus, it doesn't matter if we've got the positive or the negative, we're still going to get the same result because x is being squared. So let's start with plus or minus 1. If x is 1, 1 squared is 1, and 1 over 1 is 1. Same thing if x is negative 1, doesn't matter. Now here, if we take 0.5, or 1 half squared is 1/4, and 1 divided by 1/4 is 4. Now for 0.1, that is 1/10. 1/10 squared is 1/100th, and 1 over 1/100th is 100. Right? 1 over something is just the reciprocal, so 1 over a 100th is just 100. Now if we take this is 1/100th. If we square that, that's 1/10,000th, and 1 over 1/10,000th is 10,000. You can always use a calculator for these if you are struggling with 1 over a fraction. Just plug in the decimals and you're good to go. Now this is 1/1000th. 1/1000th squared is 1/1,000,000th, and 1 over a millionth is 1,000,000. And so if we look at what's happening as x gets closer and closer to 0, the values of our function are growing astronomically. Now, since they don't approach a single number, these are not getting closer and closer to a real number, our current definition of limits would say that the limit doesn't exist. However, we do have a special notation to indicate this particular behavior, because while these numbers aren't getting closer and closer to an individual real number, we can see that they are growing bigger and bigger and bigger. And if we were to continue and pick even smaller numbers, we would end up with an even bigger outcome. If we have 1/10,000th and we plug that in, we end up with 100 million, right? These numbers are getting astronomically large. And when this happens, we say that the limit is infinity. And we write the limit as x approaches 0 of 1 over x squared is equal to infinity. Now, this doesn't mean that we are regarding infinity as a number. It's not a real number, it is a concept. And it doesn't mean that the limit exists in the traditional sense of the functions getting closer and closer to a number. What this expresses is the particular way in which this limit doesn't exist. It's saying that this function can be made as large as possible by picking values of x close enough to 0. And if we look at the sketch of a graph of this, we'll get an idea of why this makes sense. Now, of course, this is just a rough sketch of the graph. I am not a robot, I'm not perfect. This was done by hand. But if you look at this graph and you look at what happens on both sides of 0 to the y values as x gets closer and closer to 0, we can see that there is a vertical asymptote here. And the function, as we get closer and closer to 0, is going to continue increasing unboundedly, meaning it's never going to stop at a certain point. It is going to keep going up and up and up infinitely far. Now, I have another question for you. What about the limit as x approaches 0 of negative 1 over x squared? Is that also going to equal infinity? Now, here's the thing. If we put a negative in front of this, what that does is it makes all of these values negative. And in fact, if we were to look at the graph of this, the graph of this would be a vertical reflection. Just going to kind of sketch it down here. It's actually going downward down here. And so in this situation, we would say that the limit as x approaches 0 of negative 1 over x squared is equal to negative infinity, meaning that the function is decreasing without bound in the negative direction towards infinity. So we can have positive infinity or negative infinity being a limit depending on what's going on. Now, I want to look at one more example that's going to be slightly different as well. What about the limit as x approaches 0 of 1 over x? Now, in this case, we could make a table of values, but to save time, I want to look at the graph because this is a graph you've almost certainly seen before. Right? Here we go. And so if we're looking at what's happening as x approaches 0, we actually have different things on the left side and the right-hand side. On the right-hand side, if we wanted to look at the right-handed limit, it does look like that limit is equal to infinity. We could say the limit as x approaches 0 from the right of 1 over x is positive infinity. However, on the left-hand side, as we approach 0, we end up having our y values approaching negative infinity. So the left-handed limit of 1 over x as x approaches 0 is negative infinity. And because those two limits are not equal to each other, and we have different behavior on the left and right, that means that the two-sided limit does not exist. Now, we've seen the connection here between limits equaling infinity and negative infinity and situations where we have vertical asymptotes. And in fact, this is how we can define a vertical asymptote. The line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. And these statements involve the limit or the right-handed limit or the left-handed limit of the function equaling either positive infinity or negative infinity. If any of these limits, the right-handed, the left-handed, or the two-sided limit, as x approaches a, equal either positive infinity or negative infinity, that tells us that we are having a vertical asymptote. Previously, we had learned that vertical asymptotes were vertical lines that the graph was getting closer and closer to, and that can be a definition, but it's a little hand-wavy. What does closer and closer to mean mathematically? But here, we actually have cut and dry definitions of whether or not something is a vertical asymptote. If the limit, either the two-sided limit, the right limit, or the left limit, is positive or negative infinity, that is what guarantees us a vertical asymptote. That is how we define vertical asymptotes using calculus.